So as I was saying, there are a lot of things in the neuron cell bodies, including a lot of ribosomes in order to synthesize a lot of proteins for neurotransmitters, and a lot of mitochondria to synthesize a lot of energy for these action potentials, for these, for the neurotransmitter creation. And when we see this histologically, when we see a bunch of dark staining stuff in a neuron cell body, histologically we just refer to that as Niesel bodies. It's just a term you'll encounter in the literature every once in a while. Yeah.
It's literally anything that's stained.
Yes. So the free ribosomes, rough endoplasmic reticulum, it stains really dark. It looks kind of gunky. We just call that Niesel bodies. Yeah. Yep. Good question. Thank you for the clarification. So again, on this slide, what we're looking at is dendrites that have had their dendritic spines tagged with radioactive isotopes, as I understand it, the method that was used here. And this gives you the concept of how high a number we're actually talking about when we talk about neuron-to-neuron connections. It is astronomical numbers. How many neurons are talking to other neurons in your brain? As many as there are stars in the sky is what we're talking about. So again, this information goes one way. There's an input end on the dendritic end. That information gets processed at the cell body, and then it gets, a word we're going to use is summated at the axon hillock. So again, if we go back here, we see how many inputs we're having. Essentially what these inputs are telling this neuron is yes or no, excitatory or inhibitory, fire or don't fire. And it's hearing thousands of voices, and it's going to add all of those yeses and nos together, like voting for a president, and it's going to say at the axon hillock, yes or no. That axon hillock is going to initiate a series of action potentials, and that's the physiology we're going to go into detail about, is what I mean by action potentials. The end result of action potentials firing is that neurotransmitters will be released. You can't see my highlighter. Neurotransmitters will be released from the axon terminals. Question.
What makes it say yes or no?
What makes it say yes or no? More excitatory input than inhibitory input. And hopefully by the end of the day, that statement will make sense. I know it doesn't make sense right now.
So more excited,
more excitatory input at the dendritic end compared to more inhibitory information at the dendritic end. What we're going to learn ultimately is that some neurotransmitters are excitatory and some neurotransmitters are inhibitory. So for example, acetylcholine that we already know about, that is excitatory. It causes depolarization of the muscle cell. But there are other neurotransmitters aside from acetylcholine, like GABA. The sole purpose of GABA is to shut things down and stop them. And frankly, you need as much inhibition as you need excitation in your brain. If it was all excitation all the time, it would be very bad. If your muscle cells were always firing, you'd be in a tetanic contraction, and it would be bad. So having those yeses and nos is very important to functioning. Yes?
Is that what happens with seizures?
That's part of what's happening with seizures. What we'll ultimately say seizures are runaway synchronicity of multiple neurons in a region. These neurons should not be firing altogether, but they are for some reason. And frankly, for some reason, we don't know what that reason is exactly. Just overexcitability of neurons in a specific region. So it's
even if it's a grand mal seizure,
it's just widespread. Yeah.
What about with epilepsy? Do they know? Is it just like
same concept?
Oh,
yeah.
Okay.
What's that? Yeah, we really don't know. We can measure the electrical changes that are happening in regions. We can do fMRIs and calculate that there's more excitability in a specific region for different types of seizures being in different types of regions and different levels of being widespread. We don't know what sets all of these neurons off at the same time. What the physiology is. Suddenly, all the axons said yes. All the axon hillocks said go. Yeah. Yeah, it's really interesting patho. But. So again, that summation of yeses and nos, summing, yes, 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 no, no, that's more yeses than nos, Yes, we're going to fire action potentials. We're going to release neurotransmitter. You already know about synaptic knobs. They're also known as the end of the axon terminal, the terminal button, and if you're feeling French, terminal bouton. Axon collateral, some axons will split. Typically, like I said, there's only one axon. Occasionally, you'll get one that splits to do something else. And really, that's as far as we're going to get with axon collaterals. Typically, we're just going to talk about our standard structure of a neuron. And if you have a particularly sadistic neurosciences instructor, they'll insist that you use the word perikaryon to refer to a neuron cell body. I will never make you refer to it as a perikaryon. It might show up in literature or among sadists. That's about it. All right, we're back to where we were before I got cut off. Structural classification of neurons. We use one sort of standardized view of what a neuron looks like, and it looks mostly like this one down here. This is what we're actually going to call, multipolar is a bad example, a pyramidal cell that has dendrites on one end, then an axon, or sorry, a cell body, and then one axon for the most part, right? That's what we've been looking at so far. The truth is that you've got a couple of different ways to organize your neurons. We're just going to mention it here. We're going to see these guys, these unipolar neurons, in one system. We're going to see them in the sensory part of your nervous system for the most part. Otherwise, we're going to see these. We're not really going to worry about bipolar neurons as much. Again, they exist. They're just not going to be our main concern. For the most part, you can just think of neurons this way: input, summation, output. In this unipolar structural classification, you have input over here at the dendrites, and then you have this long process that makes it to that cell body. You still have an axon hillock, and that's going to summate, and then that action potential will spread down the rest of this axon. It's still unidirectional. I would actually argue with this textbook that this part is an axon. It may be myelinated like an axon, but we shouldn't be necessarily propagating an action potential. It's arguable, it's debatable. Calling that whole thing an axon is weird. So unipolar just means that the cell body has one single short process. The dendrites are way over here, and the axon goes in an anterograde forward movement. Again, our most common thing is many dendrites and a single axon. That's going to be our star of our show. That was structural classification. Here's functional classification. You're going to have sensory neurons. You're going to have motor neurons, and you've already seen your motor neuron. That's the one going to our muscle cell. And in the central nervous system only in the central nervous system, you're going to have a third type. It's going to be an interneuron, a neuron between neurons, interneuron. If you're paying close attention, you might notice this unipolar neuron right here. The sensory neuron has a cell body here, and it has one process, and then there's an input transmission. It gets summated in the cell body, and then that information is sent towards the central nervous system. Then it makes it to an interneuron, which has our more multipolar structure that we're more used to. The job of that interneuron is going to be to communicate between sensory and motor. That's all. It's going to modify it. It's going to ultimately help you understand it. It's going to give you greater consciousness. So really primitive animals like jellyfish that do not have a centralized nervous system, they have what we call a loose nerve net. They have nerves. They do not have any interneurons. They have no conscious awareness of the fact that there's food nearby or they are being touched. They only have sensory and motor. That sensory motor says, I'm being eaten, I move away, or there's something to eat, I eat it. And there's no interneuron to modify that or give them awareness of it. So the interneuron we're going to find only in the central nervous system, only in organized, more sophisticated animals like humans that have brains and spinal cords. And it's going to give us more information about our experience. Here's another word for you. Very important vocab words that do not only apply to the nervous system. Afferents and efferents. You could say afferent and efferent if you really wanted to. I enunciate afferent because for me, a means arriving to. And efferent, that E is for exit. It's going to exit. The afferent, in this case, in the nervous system, is going to arrive at the central nervous system. The efferent is going to exit the central nervous system. And again, this is why the spinal cord being central nervous system starts to be important. The spinal cord is central nervous system. You can tell because there's interneurons. The central nervous system is the only place you have interneurons. Any questions so far? All right, then let's move on to our good friends, the glia. They are awesome. What they can do is outstanding. You have 4 major types of glia in your central nervous system and 2 in your peripheral nervous system. For a grand total of 6, there's going to be some overlap of functionality between them. Hopefully by now you can recognize your neuron cell up here, and you've got many dendrites in this region, and you've got 1 axon. You've probably heard of the myelin sheath before, yes? What's the context you've heard of the myelin sheath in? What's myelin? What do you know of myelin?
Like
Protective, absolutely. It's a protective barrier.
connective tissue, isn't it?
It is not made of connective tissue, and that's relevant. It's a relevant point of clarification. So, myelin is made of glia. Both in your central nervous system and in your peripheral nervous system, you will have dedicated glial cells. They are nervous cells because glia are a type of nervous cell. And the job of that cell is to wrap the axon in a myelin sheath. That myelin sheath is just an extension of the cell itself, wrapping around it many times. It serves as insulation. There is literal electrical activity happening. So we need to electrically isolate this neuron from this neuron so that this neuron doesn't fire just because this neuron does. That's part of it, and it is protective, and it helps to maintain the axon. And in the event that that axon is cut or injured, it is entirely dependent on the myelin whether or not it's going to be able to grow back. One thing we're going to see is that the myelin sheath looks different in the CNS compared to the PNS. And that difference is what gives us the different ability of your brain cells to regrow, which is not much ability at all, versus your peripheral nerve cells, which have a certain amount of ability to regrow after they're damaged. So that's number 1, myelin sheath. Our myelin sheath in the central nervous system, it's a big word, it's coming up here in a second, oligodendrocytes. Yeah, I know, it's a big one.
That's the myelin sheath.
The myelin sheath in the central nervous system, those cells are known as oligodendrocytes. Our next CNS glial cell is our friend the astrocyte. What's astro?
Star.
Star. It's a star-shaped cell. It participates in the blood-brain barrier. That's the major one that you need to learn right now. As a side note, it also helps with neurotransmitter clearance. It's not as big a deal for you right now. If you don't have room for it, you can leave it out. If you've got to have headspace for stuff, leave it out. When you think astrocyte, think blood-brain barrier. What do you guys know about the blood-brain barrier right now? Do you know anything?
It's what allows certain
Yeah.
toxins to be injured.
Exactly. It is selective and it's protective. So not everything that happens in your body is also going to happen in your brain. If you have a blood sugar spike in your body, you are not going to have a blood sugar spike in your brain. If your brain spiked blood sugar, you would die really quickly. If you had low blood sugar in your brain, you would die really quickly. If you had the level of bacterial exposure in your brain as you have in your bloodstream, you would die pretty quickly, and so on and so forth. It is protective. We've also got microglia. A microglia is actually just a modified white blood cell. Because you have a blood-brain barrier, you cannot have the same blood cells that work for the rest of your immune system working in your brain. In most systems that we look at, we're going to find some kind of modified white blood cell that hangs out there, and if a bacterium does make it through the blood-brain barrier, it's going to be there to clean it up. Or if there's some kind of damage, it's going to be there to clean up any cellular wastes that are left behind from an injury. So it's just an immunological cell. It's the cleanup crew. And our last guy of the central nervous system is called the ependymal cell. Ependymal is another way I've heard that pronounced. Pronounce it either way. These cells secrete cerebrospinal fluid. It's the stuff you're going to test when you do lumbar punctures. CSF, cerebrospinal fluid. Yes?
So if someone gets injured, I don't know if it's a condition or like there was a woman I knew, her husband was leaking cerebrospinal fluid into his cavity. Is that because it's just get injured?
Yeah, there's got to be some kind of injury. We'll talk about the flow of CSF later. You will have to know it in detail, don't worry. Yes, there are a number of places where you can injure the barriers that have CSF in them.
That's bad, right?
Yes.
Yeah, you don't want to be leaking CSF. It's not a good thing, most likely.
I think you should die at a much younger age. At least that's what.
Yeah. I mean, I feel like it depends on what the leak is and what the cause of the leak is and the severity. If it's something you can find and repair, then it should be fine.
Yeah, I don't know more about it with Rick said, but I do know that he was like dying young.
Okay, interesting. Might have been some congenital thing. I'd love to hear more about it if you find out more about it. Okay, so what are astrocytes? What do you think of when you think of astrocytes?
Blood-brain barrier.
Blood-brain barrier. What do you think of when you think of ependymal cells?
This
CSF. What do you think of when you think of microglia?
white blood cells.
White blood cell cleanup crew. And what do you think of when you think of oligodendrocytes, everybody's favorite word? Myelin sheath. Excellent. There's two more of the peripheral nervous system. The good news is that one of them is another form of myelin sheath. Your textbook calls it a neurolemmocyte, and that's a pretty good standardized linguistic name for it. I call it a Schwann cell because that's the old school name. I'm going to write it up here. It's SCHWANN, Schwann.
It's the PNS form of myelin sheath.
Yes, the peripheral nervous system form of the myelin sheath is known as a neurolemmocyte or a Schwann cell.
On the exam, can we write Schwann versus? Okay.
Yes, you should be able to recognize both.
And that's what the Myelin Sheaths are.
The Schwann cell or the neurolemmocyte, that's the same thing. It is the myelin sheath in the peripheral nervous system. Finally, in the peripheral nervous system, When you have collections of cell bodies in the nervous system, in the peripheral nervous system, you may find satellite cells around the parakaryon, around the cell body in the peripheral nervous system. They're going to support that neuron in the peripheral nervous system. This table is on your worksheet today as well. You got to know these guys. Astrocytes, again, they have this, the way that they create that blood-brain barrier is what we call perivascular feet. They have foot processes that, this is to only show it partially covering that capillary. Ultimately, we're going to completely cover that capillary bed in perivascular feet. Ependymal cells secreting cerebrospinal fluid. We're going to find them lining ventricles. A ventricle is a space in the brain. Your brain is not solid all the way through. Your brain has cavities, and it's a really good thing that your brain has cavities. We're all airheads, and that is a good thing. It makes us more lightweight, and it means that if our brain starts to swell a little bit, it's got space to swell into. Very important. It's also a very limited space that it has to swell into, so after a certain point, you lose room to keep swelling, and you start crushing your cells. So we like our ventricles. We are big fans of ventricles. That layer of ependymal cells that lines the ventricles, we're going to call that the choroid plexus. We're actually going to be able to see it when we dissect sheep brains. We're going to be able to peel off this kind of gunky stuff inside of the ventricles, and that's going to be your choroid plexus. It's a visible structure by the naked eye. And it is made of ependymal cells. Their job is to release cerebrospinal fluid. Microglia, they are motile. They are phagocytes. What's a phagocyte? They eat. They eat things. They remove cellular debris from dead or dying cells. And if an invader gets in there, it can eat that too. Good. Yeah. Let's compare and contrast oligodendrocytes versus Schwann cells. Oh, I gave it a C. I guess it's just SHWANN. In the central nervous system, one oligodendrocyte myelinates multiple axons from multiple neurons. You see this one cell body here, and then you see multiple units of myelin. You have a piece of myelin, and then you have a little break, and then you have a little piece of myelin, and then you have a little break. And then over on this other axon, there's a piece of myelin and a little break, and a piece of myelin and a little break. So one oligodendrocyte, multiple myelin sheaths. Whereas in the peripheral nervous system, one Schwann cell wraps around that axon and makes one unit of myelin sheath. This is very clinically significant. This is what's going to allow your peripheral nervous system to regrow axons.
One neuron.
One neurolemmocyte, or Schwann cell, is going to make up one myelin unit.
And because it's one cell, it's just easier than trying to fix one part of the cell, is that why?
You'll see why.
Okay.
They're going to play a very, very unique role.
Okay.
Yeah. It's cool. It's awesome. The role they're going to play. We're still recording. We went past the 15-minute mark. Yay. Don't have to repeat myself. And again, satellite cells are going to be flattened cells around cell bodies in the peripheral nervous system. They're just going to support and protect it. That's all we're going to do with satellite cells. There's that neurolemmocyte, again, formally showing you one cell, one myelin unit. One cell, one myelin unit. One cell, one myelin unit. Now see, now it's got a C again. That's great.
I thought I had a C.
Yeah, that's probably a typo in the other one. Another compare and contrast. Oligodendrocytes, one cell, multiple myelin units. Schwann cells, one cell, one myelin unit. One cell, one myelin unit. There's one more thing that myelin does, aside from insulation and protection of the axon and regrowth. That's super important. It actually speeds up the rate of action potential propagation. This is a word. This is the definition for saltatory conduction. The myelin sheath improves saltatory conduction, which is to say that the myelin sheath increases the rate at which we send action potentials down an axon. Again, you don't know what an action potential is yet, that's okay. We'll come back to this.
So, saltatory conduction, myelin sheath.
Improves the rate of saltatory conduction. The myelin sheath improves the rate of saltatory conduction, which means it improves the rate of action potential propagation. What this is showing you is that Schwann cell wrapping itself around the axon over and over and over, so that in order for something to get into the axon, it's actually got to go through all of these plasma membrane layers. Like flapjacks. Like seriously, that's a lot of layers to get through for anything electrical that could happen, for anything bacterial that could happen. It's a lot. So nothing's getting in there. All right, damage. Woohoo! Here's what happens in your peripheral nervous system. You'll notice that we're in the peripheral nervous system because you have one Schwann cell for each unit here. So there's some kind of trauma. Somebody took a scalpel blade to your radial nerve. Sue that doctor. How dare they? What we're going to have is at the site of the axon injury, the end of the axon is going to seal and it's going to swell up into a little bulb. Downstream of the trauma, on our way to the target organ, those neurolemmocytes, those Schwann cells, are going to actually roll up into little balls, and they're going to act as signposts. So I'm going to do a little acting thing here and try. It's not going to play out for the listeners at home. I have a severed axon. This is my swollen end bulb. And there's a bunch of signposts on the way to the target organ. It's going to be that table over there. I'm completely blind. All I have is a chemical environment around me. What I'm going to do is I'm going to grow little processes from this swollen end bulb. And I'm going to look for a signpost. And if I'm fortunate enough to find one, I'm going to grow my axon a little bit further out to that signpost. Now the cell body is actually going to stay here, but I can't grow my arm, so I'm going to move this way. So now we've made it to a new signpost, and I'm going to repeat that process again. I'm going to stick out little foot processes and look for another signpost. And if I find one, I'm going to grow towards it. And it's going to keep going like that. And if I keep finding signposts all the way down to the target organ, then I can reinnervate that target organ, that muscle cell, or whatever it is, that gland. If the trauma is so bad that at any point I am unable to find a signpost, it'll just stop. And let's say we cut multiple axons. If I find the wrong signpost, I might grow down here, and I might end up innervating the wrong thing. That happens in the peripheral nervous system when you regenerate neurons. Sometimes you get cross-wiring. Yes?
What does that look like neurologically on a person when it attaches wrong or when it's going to attach?
Has anybody in here healed from nerve damage before and got weird mixed signals? I have. It's great. It's weird. You've got one? Do you have a story? You look like you nodded a little bit.
Oh, I had some knee surgery and they cut one of the nerves and I ended up massive pain in one side of my knee when I do something to the other saw it. It was just,
Yeah.
yeah.
Yeah, it can just be like, touch that, feels like that's being touched. Or it can be erroneous pain signals, or it can be any number of weird things. Yeah. I have a big patch of nerve damage, that's why I'm pointing right here. Right here from a car accident, my seatbelt went kind of sliced everything there. So I still have weird signals from here. It's super strange. I call it the neural equivalent of the sound eh. That's what it feels like. Yes. The signpost is the rolled up Schwann cell. That's the role Schwann cells have to play. They're the signposts.
Where does it say that?
They're right there. It's not describing it as well as I am in your book.
Okay.
Yep. So it's just going to keep looking for it. Once upon a time, a professor of mine showed me a video of this happening, and I cannot for the life of me find this video. It's outstanding, though, the little foot processes that it grows, trying desperately to find the next Schwann cell.
And that only happens in the peripheral nervous system.
Yes,
The
this is
CNS
how.
does not.
CNS typically does not. What we find is, one, you have oligodendrocytes arranged like that, so you don't have as many signposts. They're not serving just this axon, they're serving multiple axons. So you won't have as many signposts. The weird thing, the messed up thing, is you actually seem to have chemical signals. Some very clever person named this chemical no-go, because they're being a jerk, that actually discourages that swollen end, that Wallerian degeneration, from creating the foot processes in the first place. So you actually literally have a substance in your brain that says, don't do it, don't regenerate.
Oh, wow. That's messed up.
It is. But on the other hand, think about what's happening in your peripheral nervous system. We're going into completely hypothetical situations here. I'm going on a weird tangent here. Okay, so he gets weird pain on the wrong side of his knee, right? Because it cross-wired when it regrew.
In your brain could be far worse.
It could be far worse in your brain, right? Like you think you're turning left on the highway, but you're turning right on the highway. So evolutionarily, yeah. Or you misinterpret people's emotional signals to you, or you get in a fight with a lion, whatever. Like, you're not going to live long if you get cross-wired in your central nervous system. So evolutionarily, there might be an advantage to not regrowing those axons. Also, because those cells are not capable of mitosis, they are much less likely to become cancerous. The cells that become cancerous in brain are going to be glial cells. That's why you hear the term glioblastoma, for example. Yes, that's where that's from.
Why does cross-wiring happen?
Because the signposts are, you probably didn't just sever one axon, you probably severed multiple, and it doesn't differentiate between that Schwann cell and that Schwann cell and that Schwann cell. Yep. Feeling good about that one? Did that answer your questions? It's interesting stuff. It's intense. Go crazy about it. So in the central nervous system, yeah, you can have some recovery. It's dependent a lot on age and brain plasticity, is what we'll say. But I'm going to cut it off there because we got to get going on this. We can talk about it later if you want. All right, action potentials. We did that myelin sheath thing. We did Wallerian degeneration. Just like your muscles have an epimysium, paramysium, and endomysium, your bundles of nerves are going to, especially in the peripheral nervous system, your nerves are going to have epineurium, paraneurium, and endoneurium. And it's going to follow pretty much the same pattern. Just like epimysium surrounded the entire muscle, epineurium surrounds the entire nerve. Just like muscle fascicles had paramysium, fascicles, bundles of individual axons, are going to be surrounded by paraneurium and endoneurium around each individual axon, in addition to the myelin sheath. So there's even connective tissue around the myelin sheath. The purpose, again, of those connective tissue layers is going to be to distribute blood supply. Any questions there? It should be a really familiar pattern at this point. Histologically, there's a reason we never put transverse or longitudinal sections of peripheral nerves into our histology slides. Does that look like anything else to anybody from?
Yeah, smooth muscle.
Yeah, it looks a lot like smooth muscle, doesn't it? It's like a cruel, cruel thing to do to a person. So that's why that wasn't in there. Yeah, it looks a lot like smooth muscle. To me too. If you handed this to me, I would be like, is that smooth muscle? And I still wouldn't know. But if you do a transverse section of a peripheral nerve, you'll get that bundling pattern. And these spaces right here, those are blood vessels. All right, synapses. Presynaptic neuron. You have the neuron before the synapse. That's the one sending information along. That's the one that is going to release neurotransmitter. Then you have a space known as the synaptic cleft. Then you have the postsynaptic neuron, and that's going to be, that structure right there is the dendritic spine. And that dendritic spine is going to have receptors for the neurotransmitter released by the presynaptic neuron. This is structurally incredibly similar to your neuromuscular junction, right? The difference is instead of having a motor end plate right here on a muscle cell, you have a dendritic spine on another neuron. Can you see over there?
Kind of. Skeleton's a little bit in the way.
Gotcha. Okay. These are considered chemical synapses. What we mean by chemical synapses is that a chemical is released. Chemical is a very vague word. It can mean anything from an ion to a complex molecule to a complex protein. The chemical is released into the space. It diffuses across the cleft. It binds to a receptor, and that receptor does something to the postsynaptic neuron. Just like at your neuromuscular junction, that neurotransmitter depolarized the muscle cell. We're going to contrast that with electrical synapses, which mean that the electrical state in one cell is shared with the electrical state of another cell via gap junctions. This is, for example, how those cardiomyocytes are going to work. So yes, there was an electrical impulse that caused release of this chemical, but because that communication happens via a chemical, such as acetylcholine, we call it a chemical synapse. So do not make the mistake of calling this an electrical synapse. Electrical synapses can be found in smooth muscle cells. They can be found in cardiomyocytes. Those are really going to be our prime examples for electrical synapses. It's on your worksheet today. Looks like it's time to start with action potentials. Are we feeling ready? It's exciting. Yay, electricity. Has anybody ever worked with electrical stuff? Done any electrical engineering? Used a voltmeter? Nobody's used a voltmeter before? Okay, it's okay. When you're talking about electricity flowing in a wire, in your walls, in your house, you're talking about the movement of electrons. And they're generally going in one direction through that wire. When you're talking about electricity in an axon, you're talking about the movement of ions into and out of the axon. These are related to ions as well. For every positive, there's a negative, so electrons are moving too. They're not moving along in one direction, they're moving in and out. So it's an axon. We're going to call this the extracellular environment. And this will be the intracellular environment. All right, here's your action potential. It'll make sense. Big picture, what we're going to have is a neuron at rest, a neuron that depolarizes, a neuron that repolarizes, and then it returns to rest. What I mean by depolarize is that it's going to become more positive. Positive ions are going to rush into the cell and electrically make it more positive. What I mean by repolarization is that your cell is going to usher those ions back out and reset it back to a highly negative state. At rest, your neurons are very negative. The environment inside of your neuron is negative compared to the environment outside of your neuron. The intracellular environment is approximately negative 70 millivolts when compared to the extracellular environment. This is a measurable thing. We can do it with math, or we can literally do it with the same kind of voltmeter that your electrician uses on the cables in your house. Not joking. So before we talk about how an action potential can fire, we have to talk about what the neuron is doing at rest. And we've got to look at some really great plasma proteins. This is why we really emphasized plasma proteins back in the day. We also need to review gradients. Who remembers a gradient? What's a gradient? From high to low. Things move from high to low. They want to move from high to low. They're going to diffuse from high to low. If they have a way to go from high to low, they're going to go from high to low. In what state, what do we require in order to move something from low to high?
ATP.
ATP, absolutely. And what kind of protein channel type thing is going to enable you to pump things against their gradients? Sodium, potassium, ATPase. Pump is what your brain is going to, and it's correct. A pump is what we're looking for right now. We need a pump. We're going to have some pumps. We're going to have some channels. We're going to give all those pumps and channels names. We're going to give all those pumps and channels roles. There's going to be pumps and channels that work at rest, and there's going to be a handful of new channels when we do the action potential. There's a lot of players on the field. When we're talking about action potentials, this is where we are. We're at the axon. You got a bunch of pluses and minuses up here. They're summated at the axon hillock. The only places the action potential is going to fire is along the axon. You guys may have not had chemistry for real. So electrically, positive likes to go to negative. If you cram a bunch of positive into one area, it's going to try to diffuse away from itself. It's going to try to go to a negative area. What we're going to end up with is both mechanical gradients, physical gradients. There's just too much of this stuff here. I want to go somewhere else. And also an electrical gradient. So here are our channels, and here is our pump. Our pump is a sodium potassium ATPase pump. That's Drake. Let's see if Drake's working today. I don't think Drake's working today. I know it's just going to show. I don't think I can bring up the video for you guys. That's so lame. All right, we're going to watch the video over break because you've seen it before, but it's worth looking at again. Drake doing his little dance. Sodium potassium ATPase pump moves 2 potassium into the axon and 3 sodium out of the axon. He's a pump, so is he pumping with or against gradients? Against both gradients, which means that there's more potassium in here and there's more sodium out here. So neither of these things want to go in the directions they're going. We're using cellular energy to pump these things against their gradient because we need to build a mechanical gradient. The end result of building the mechanical gradient with these large positive ions is that inside of the cell, electrically, it's going to be more negative than outside of the cell, where all of the sodium is. Sodium is the bigger one. It's more positive. I think sodium's the bigger one. Yeah. There's 3 sodium, so there's a major effect of how positive they are outside of the neuron. Inside, it's going to be negative. It's going to be negative 70 millivolts. In addition to the sodium-potassium ATPase pump, you also have leak channels. You have a leak channel for potassium, and you have a leak channel for sodium. They are not going to have as large an effect as the sodium-potassium ATPase pump. If you've got a leak channel for sodium, is sodium going to go up or down its gradient? Down. So even as Drake is pushing all of the sodium out of the cell, leak channels are letting some of it back in. Yeah, it's just kind of leaky, right? There's a literal microscopic voltimeter telling you that we're at negative 70 inside of the cell. All right, here's the clinical term for this. When the mechanical gradient for potassium is in equilibrium, the electrical gradient is at negative 70. Because of the movement of potassium, because of it trying to go down its gradient and being pushed against its gradient, and being very permeable, moving in and out a lot, the electrical gradient becomes negative 70. So Drake's doing what? Sodium potassium ATPase pump does what? Moves 2 potassium in, 3 sodium out, uses 1 ATP for that process. So he's helping to build gradients.
Mechanical gradients, right?
Mechanical gradients, absolutely. You also have a potassium leak channel. Which way is potassium going? Down its gradient, and it wants to go out of the cell. And you also have a sodium leak channel, and sodium wants to go where? Into the cell. Another thing that makes this very negative, maybe you're catching on right now that both potassium and sodium are positive ions, so how can that make anything negative? Every once in a while somebody catches that. Large negative proteins. We're also not even talking about chloride ions and what they're doing. They're doing a thing too. We're just not talking about it. Large negative proteins inside of the axon help keep this very negative. Because of these pumps and channels, the end result is that inside of the cell is negative 70 compared to outside of the cell. A resting neuron exists at negative 70 millivolts. Even without a voltimeter, there's a mathematical formula that you do not need to use at any point in your life, but that I've had to use to do this. We can use the Nernst Equation to mathematically determine what we call resting membrane potential, the millivolts of difference between inside and outside the cell when a neuron's not firing is the resting membrane potential. And again, you don't need to use this, but it's a function of the concentration of potassium outside of the cell compared to the concentration of potassium inside of the cell, related to the charge of that ion and a couple of constants and the temperature as well. One more significant thing that I specifically have to define. At rest, potassium is the most permeant ion. That means the ion that is moving in and out most, and determining that number, that negative 70, is potassium. At rest, potassium is the most permeant ion. And that's a good breaking point. Let's go ahead and go on break.